Dr. Sahin from the University of Bristol. So she's also was leader in the field of schematic analyzing for detectors, and let's see what she has to say about it.
Hello.
Yes.
Okay. Thank you, Jorge, for the introduction. Today I'm going to talk about designing the single photon detectors in a waveguide cavity. I think Will made it very easy for me to just smoothly slide into the detectors because he gave a lot of background into it. And this work has been done in Bristol mainly by the PhD students Nicola, Mac, and Ben. And I think you will see their faces at the end of this slide as well. So I don't know if there is a lot need to motivate you for why we need single photon detectors. We have been talking about all the applications of quantum photonics from simulations to communication throughout the week. And all these things have very stringent requirements in terms of efficiency, jitter, and speed basically. And those quite stringent requirements are not very easy to satisfy unless you have a detector, which is SNSPD. So what SNSPD stands for superconducting nanowire single photon detectors. So these detectors, as well already explained, are the best detectors to date. You can just take off the shelf and basically plug into your experiment. And the efficiencies currently has been demonstrated beyond 90%. I think as high as 96% you can see in the literature. And the detectors also have very fast speed, so that time in the order of few nanoseconds. And you can also find this number down to 4 to 6 nanoseconds in the literature. So the dark count as well just explained could be as small as millihertz. So there is no reason why you cannot get that number quite low if it means sacrificing sometimes your efficiency, or even if you have very good filtering in your cryostat, you can get very high efficiency as well as with very small dark count. So the jitter is something you have just learned as well as well. And the very recent paper just came out this week, talks about how to get this number down to 3 picosecond from MIT. And you can find it on this paper in the archive now. And the last thing maybe to talk about is they have very long spectral range. And we know they are sensitive from anywhere visible, maybe even like UV, up to 5 micron, because we can only measure them so far up to 5 micron. And again, you can read about it on this paper. So in standard SNSPDs used to be just meandered wires, and you put them into very narrow, nanowire structure, and then bend them around so that you get very large area, which couples well with your fiber, right? Because you want to make sure that you have the maximum overlap between your photons and the detector. So this has been the way of doing it from the first time it has been demonstrated by Goldsman and his co-workers. And typically they have the area of 20 to 20 maybe micrometer square. So this is quite a long device. As you can see, it is about 200 micron or maybe even longer. So one thing about these detectors, of course, because they are very thin, this is not very efficient of detecting your photon. So what you do, you generally also create a cavity underneath, so you make sure that your photon travels back and forth, and then eventually you absorb it. But again, you still have this long meandering on it. So, sorry, it's the wrong way around. So what we did back in 2014, we did a study about these wires, because we were using this niobium nitride, which is a crystalline superconducting material, and you always end up having very low yield with those detectors. So you maybe fabricate hundreds of them, and then you get maybe, if you're lucky, 10% of them working at the end of the day. And it's a good PhD project, so you're in the lab all the time measuring and getting the best of it. So what we did, we put very short nanowires between these bow tie structures, as you can see, and we varied those lengths from as small as 100 nanometer to 15 micron. So as you can see here, with the length increasing, due to some sort of inhomogeneity you have in your wire, you create a constriction in it. So what happens eventually, the critical current decreases with your length. And probably eventually it actually saturates because the probability of getting these constrictions are going to be statistically quite similar. So you can see this is similar on gallium arsenide and also silicon. There is a little maybe slow decay, but eventually you have the same trend. And this is only because niobium nitride has very strong requirements of the good crystalline deposition, and that's very difficult to get in the very thin film layer. And you can easily see that this is reflecting itself in the efficiency here. So if you can bias your wires with higher bias current, you actually end up seeing a lot higher efficiency here. And the lower the bias is, the lower your efficiency. So this motivated the community quite a lot. They said, how can we get around this? And one way of doing it is, of course, shrinking your nanowire, and it could be putting it some sort of cavity or some sort of traveling wave structure where you have higher absorption because of tight mode confinement. So what we did back in 2011, for example, we demonstrated the first integrated waveguide detectors on gallium arsenide, and here we could go down to 30 to 100 micron long wires. But this problem still exists, they are still long. So just to briefly explain how the detection is happening in this type of detectors, it's nothing different than what Walt just explained, but this time your photon goes through the waveguide, so it's a traveling wave, and then eventually it will be absorbed by your nanowire, which was already biased close to breaking switching current, and then you get this nice photon pulse. And people started doing this, integrated on various materials systems, and you can see this paper from Goldsman and Yale group, and they put the niobium nitride detectors on silicon, and they get down to, I think, as small as 20 micron with quite high efficiency. The detection efficiency they could find was above 90%. They measured above 90%, but the yield was still a problem. So this was one of the devices they could find working quite well. But it was still good. They could manage to get quite high efficiency, which is promising. And the other technique the colleagues from MIT has developed with Dirk Engman and Carl Bergen, they went for this pick and place technique similar to the nanowire technique for the quantum dots. They fabricated the photonic circuits separately, and then they fabricated their detector circuit, and they put the detector on a suspended structure. So there is, as you can see here, silicon nitride membrane, and you can under edge this structure. So when you suspend it, it's easy. You pick it from wherever this detector is, and then you can just manipulate it. So they put it on the photonic circuit, as you can see here, and they did this for 4 detectors, which still had the variance of detection efficiency around 14 to 52%. And in that way, they managed to get the best out of all the detectors they fabricated. And this is a nice technique, but this is not very scalable because, as it has been discussed previously, if you want to do this in the big scale, you need to find a way to make this a lot faster than just manually pick and place. Okay, so here they demonstrated also G2 tau second order correlation function of the single photon sources. And at this place, I think the amorphous fields started taking place. So there are superconductors which are crystalline, like the niobium nitride I've been describing, and then there are superconducting films which are amorphous. So amorphous films are good in a way that they don't require a lot of compatibility on the surface of the substrate they are put, because the lattice matching is not as important, as critical as these other materials I've been talking about. So what you can do with amorphous film, basically you can put on any substrate you have, and here, for example, they use silicon and silicon dioxide for the cavity, and then they put their tungsten silicide, and then there is also front cavity with the titanium oxide. So you couple your light from one side of it and make sure that your photon travels within this cavity back and forth and eventually absorbed. And as you can see, actually they demonstrated an efficiency of 93%. And the efficiency here, you can see there are two curves. So the higher one is the efficiency when you align the light parallel to the nanowire. So this is the maximum polarization you get, coupling. And then there is also a perpendicular polarization. You can align perpendicular to your nanowires and you still get quite high efficiency. So this is not a big problem, because especially if you have these detectors on specifically designed for this polarization, you can actually benefit from the highest efficiency. So this is about 93. I think they have shown recently around 96% using the same material. Of course, there are some drawbacks. The jitter, for example, here, as you can see, if you bias at a very high bias current, which is not that high for these amorphous films, you are still around like 150, or maybe these days around 100 picoseconds. And the other thing is, because you have very low bias current, the signal to noise ratio is quite low in this detectors. And maybe last but not the least, the operation temperature is also quite low. So when we talk about cryogenic, people sometimes say it doesn't matter, it goes into cryostat anyway, but it's important if you are working above or below 1K, because things get very complicated as soon as you move below 1 Kelvin. So these detectors generally operates below 1 Kelvin. So what we did here in Bristol, we decided we will put these detectors, nanowires, in a cavity structure. And it aligns quite well, I think, with the rest of the work we are doing here, because we use rings, we use silicon circuit quite often here, and we know quite well about it. So what we did, we put this nanowires on the racetrack structures, as you can see here. This is our bus waveguide. So you couple your light in from here, and this is your exit port. And at this point here, there is a beam splitter. So it's similar to your directional coupler. You bring two waveguides quite close to each other. So you evanescently couple your light from one port to the other. And if you satisfy the condition that your reflectivity at this point is going to be equal to your absorption within your cavity, while maintaining the phase match condition, you are in the critical coupling region. So if you are in the critical coupling regime, what happens, your photon again just goes around this cavity until it has been fully absorbed. And this absorption is of course not just the wire, it will also be your silicon loss. So there is a kind of trade-off with this design, which I will talk about. And this is just a demonstration. If you get this critical coupling right, you get your photon in, and at this area where the SNSPD is, you absorb the light, and then actually nothing comes out from the exit port. And I think the poster is removed, but there was a poster about it yesterday by one of the students. So some performances about these detectors. As you can see, you can actually play with your coupling. In this case, we are playing with the reflectivity here. So by changing your reflectivity, you can actually tune your absorption, required absorption within your cavity, and you can change your nanowire length. And we found out that the best range to work for the detectors is around maybe 1 to 2 micron here. It's not only because the absorption is getting less here, but also because, as I said before, there is a loss in your silicon, and you want to make sure that your photon is not lost before you absorb in your nanowire. So you want to make sure that you decrease the amount of circulation in the cavity. And yeah, as you can see, if you didn't have any cavity on just silicon waveguide, you needed more than 20 micron long wave detectors, nanowires. But if you have your cavity, it can be as short as 1 micron, which is a good thing. And the other thing is, because the cavity is already, it has already its bandwidth, you actually, by introducing some loss, you can modify this. So if you have very low loss, you just follow the racetrack cavity structure, but if you have a lot of loss, basically it's just creating a very low Q ring structure. You broaden this. So you can play with this bandwidth, and you can make maybe narrower broadband single photon detectors, kind of like single photon sensitive spectrometer. Also, we looked at the jitter because, as I said, the photon is going to travel within the cavity, and we want to make sure that this doesn't take too long, so that the uncertainty is not too big. And if you can see, if we, for example, design a nanowire around 2 micron with 83 micron long ring structure, we introduce about maybe 2 picosecond, but we can always go below that, below 1 picosecond regime, as you can see. So this was our simulation on the wires. Now we are at the stage of fabricating this structure. So what we are doing is we are looking at the crossing. So we need to take these contact pads on the nanowire so that we can electrically probe them. And we design a crosser which is basically just a taper, as you can see here, and a multi-mode waveguide. So the reason we wanted to do that, we tried to get something quite short because we didn't want to have very long structure in our resonator, and that's because it would add to our losses in total. And also we want to make sure that we can fabricate that within the same process we are fabricating our waveguides. That's why we came up with this design, just expanding, kind of, maybe not necessarily adiabatic, but you're expanding into this longer, wider waveguide, and then you are getting into this multi-mode regime, and you are basically imaging your input here to this point, and then you are imaging back into your narrow waveguide. So this is a perfect spot where the electric field is quite intense. You can put your nanowire, and you can still get high absorption. This is exactly what we are doing, and these crossers, according to our knowledge, are the smallest and basically quite low reflectivity and crosstalk structures we could find in the literature. And again, I want to emphasize, we don't have any extra step to create this. It's just single step etching. And this design we have studied has been already demonstrated on a different platform. So that makes us actually, I think, quite excited, because people has used the same concept, same idea of photonic crystal, and they demonstrated near unity efficiency from these detectors. The only disadvantage probably here is the photonic crystal cavity they use, because they are quite sensitive in terms of the hole size you drill and the positioning of them. And as you can see, they are quite small, like 50 nanometer or so in this region. Okay, and maybe very briefly, we also have a work ongoing at the single photon detection around 2.1 micron. This is just a very preliminary result. We put, in this case, we put an amorphous material on the waveguide just for the simulation, and we have demonstrated on silicon. We have calculated on silicon we can get an absorption at around 90% with just maybe 30 micron long waveguides. And this is only for TE polarization, by the way. So as you can see, the mode is quite tight, so we can actually absorb quite a lot of light in a very short waveguide length. And these are just some of the structures we have started fabricating These are for the grating couplers to couple the light in. And then this is the area where you couple your light into the racetrack, so directional coupler. And these are your nanowires. And I'll leave you to the conclusion. I think I don't have much time left. So if you have any questions, I'm happy to answer.
Thank you, Dondu. Questions? There's one more.
Thank you very much. Very interesting. You had a slide on the jitter due to the ring detector.
Right.
And there was like this negative linear correlation, but then there was a step change at the end.
That's just because we skip some points in between. It's very, like, we look at the discrete spot, discrete points. So if you could calculate it every possible spot in, like, points in between, you wouldn't see that discrete change.
Right, so there's nothing physical about the fact that there's...
No, there shouldn't be.
You won't do 2.1 microns. I just wondered, curious, what's happening at 2.1 microns?
So actually, we have some work ongoing on around 2.1 micron. And I think people are looking at that around, for the silicon content photonics as well as classical photonics, for example. So the reason for that is we have a lot of 2-photon absorption at 1.5, but if you go around 2 micron and beyond, especially around 2.1, 2.2, you actually don't get much contribution from 2-photon absorption.
Okay.
And that's one of the reasons, motivations for that work.
Thanks.